Hello and welcome back to Introduction to General Relativity. In the previous lecture, we introduced and discussed geodesics. Today, the objective is to also talk about geodesics and provide a second characterization, which is perhaps more intuitive, of what a geodesic is on an arbitrary manifold. After that, we're going to use a discussion of parallel transport to introduce a notion or an intrinsic notion of curvature of manifolds. But first, to geodesics. Suppose we have a manifold M and we have 2 points on M, and we also have a derivative operator associated to M. Then we can associate to any 2 points and any derivative operator in a manifold a length of the curve that joins these 2 points. So we imagine we have some curve here that joins the 2 points. We'll call the 2 points P and Q. And we can associate to such a curve a length. Of course, we need a metric. So the data of a derivative operator is roughly speaking equivalent to the data of a metric, but let's be explicit here. So we have ourselves a curve, let's call it C. We have 2 points, PQ, we have a metric, we have a derivative operator, we have a manifold, and we can introduce the length of the curve C, which we've discussed previously, intuitively in previous lectures. So the length of C with respect to GAB delta A is just defined to be the following expression. You integrate over the length of the curve the inner product between the 2 tangent vectors, between the tangent vector to the curve, along the length of the curve. So TA here is the tangent curve to C, and T is the curve parameter. So I'll draw on the picture here the tangent vector. So to any point on the curve, we have a tangent vector TA, introduced way back in the earlier lectures. And also we assume just that our metric, can't just have any metric for this expression to be well defined. We assume that our metric GAB has signature. So when you diagonalize it as a matrix, that you always get plus positive eigenvalues. So implicit here, now explicit, is that the metric has positive signature. So we can define this length, right? There's no particular problems in defining this quantity. Just integrate infinitesimal lengths along the curve. So you've got to imagine that you have this curve C and you divide it up into little pieces. You approximate each piece with a line segment, and then you use the corresponding tangent vector as the linear approximant to the curve. Then you calculate the length of the tangent vector, which is a proxy for the line segment, and then you add them all up, and then you take the limit as you subdivide your curve into little, smaller and smaller pieces, and then you have an expression for the length. Hopefully this expression is intuitively clear. So we can introduce this quantity. And what about for metrics of positive signature? So in general relativity, of course, our metric doesn't have positive signature, well, not always. So for a metric with signature, we say -1 plus da 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 plus. We have to be a little bit more creative with how we define our length. Our curve is said to be timelike if, when you compute the inner product of the tangent vectors to the curve, you get a negative number, right? That's possible now. The metric has a negative signature. If it's negative, everywhere along the curve. So, okay, it's timelike at that point, let's say, but it's got to be, this condition is going to be true everywhere along the curve for the curve to be called timelike. And we have two other kinds of curves that you're certainly familiar with from special relativity. We have null curves. They're ones where the inner product of the tangent vector is exactly 0 everywhere. And we also have space-like curves. That's where the inner product is positive everywhere. So you have three kinds of curves in manifolds with Lorentzian signature, with -1 and the rest positive, or all minuses and 1 positive, for example. So we have these three kinds of special curves, right? Not every curve is timelike, not every curve is spacelike, not every curve is null, right? It's possible to write down curves in manifolds which are sometimes null, sometimes timelike, sometimes spacelike. They're not physical, and as we'll see, they can't be geodesics, but we can certainly write them down. So you've got to understand this definition, right? It's not being for all curves. Like, it's possible to start off with a curve being null, going space-like, and then going time-like, right? I can draw that curve, but it's no particle, no solution to the equations of motion, whatever field or in special relativity, no physical solution can behave like that. So that's a forbidden, physically forbidden, but it's mathematically at this point allowed. Right? There's nothing that says that that's wrong. So I better, for the future notes, right, this is unphysical. And then I'll highlight the portion. So it commences null, it goes space-like, and then it goes time-like. So time-like is green, say, null is yellow, and space-like is blue. That's certainly a possible thing to happen, but as we'll see, geodesics cannot do that. And now that we've got these three notions of infinitesimal length, we're going to have to slightly expand, generalize, or update our definition of the length of a curve, right? Because, okay, the length of the curve still, that definition here, still makes sense when you have a null curve or a space-like curve in a Lorentzian or Minkowskian setting. But if you had a time-like curve, so that's everywhere negative, you can't take the square root of it, or if you did, you get an imaginary number, which is, you can certainly go that route. We're not going to do that, though, in this lecture course. Instead, we're just going to say, suppose we have a time-like curve. Suppose you have a time-like curve C. Well, we define, instead of the length, we call it the proper time. So if you have a time-like curve, then instead of defining the length of the geodesic, you define the proper time of the geodesic. Not geodesic, curve. Although, of course, it will apply to geodesics. Okay, so now we have a definition that covers all the cases that we're going to encounter in the world of geodesics. And, a side comment, of course, I've implied this earlier, but now let's say it clearly. So if a curve C changes from, e.g., time-like to null, or time-like to space-like, right? That's where we're going to have real problems. The length, this implies the length is just not defined. And you can have fun trying to define a length, but we are just going to say it is hereby not defined if the curve changes from time-like to space-like. That's the particularly problematic transition. And now we'll take a look at geodesics. This is in the context of geodesics. We've already introduced geodesics in the previous lecture, so we can certainly discuss the length of a geodesic. And what I'm going to argue in the coming next portion of the lecture is that a geodesic has a very, the length of a geodesic enjoys a very special property. So that's the objective now. But before we quite get to that argument, I want to make some simpler observations. So since for a geodesic, the tangent vector to the curve is parallel transported along itself, we learn that its norm can't change, right? The norm being the inner product of the two, of the tangent vector with itself, which is also known as just the metric contracted and what does that mean? Well, it's basically a proof of the statement I just made earlier that this geodesic cannot change from null to timelike, etc. Right? You can't change a geodesic. A timelike geodesic can't change to being a space-like one, and so on and so forth. And how could you convince yourself that the norm doesn't change? Well, just take the derivative of it, right? So that if you want to, why does the norm not change when we parallel transport a tangent vector along itself? So let's just do a side computation, right? Change in norm. Well, the change in the norm along the curve is the directional derivative of the norm. We've got to take the derivative of the norm as we go along the curve. But now let's substitute our expression for the norm. So it's TB delta B, and then we get GAB TA TB. And then we apply the Leibniz rule. So eventually, you'll get pretty good at these kind of computations. Then you get GAB TB delta B TA, and then you get a TB here. Oh, yeah, okay. I hope it was kind of clear. I should have not used the same index here. So let's do C's, and then we'll put C's here as well. And then there's a third term, TA delta, TC. So if you look at this, actually all three terms vanish, right? Because the first one vanishes because that's one of the defining properties of the derivative operator associated to a metric, namely that the derivative of the metric itself is 0. And now look at this term vanishes here because TA is parallel transported along itself, and the same goes for this argument here. So that's why when you parallel transport the tangent vector of a curve along with the curve, the norm of the tangent vector cannot change. And when a norm cannot change, it can't change from being a null geodesic to a time-like geodesic or to a space-like geodesic. Now you might justifiably worry, that the definition of the proper time or of the length might actually be parameter dependent, right? That would be kind of stupid. If the parameter we chose to specify where we are along the curve, if our length depends on that parameter, then that means that it depends on what mood we were in on that day when we chose our parameterization. Turns out this is not the case, of course, and I'll just give a brief argument why before moving to connecting geodesics to lengths. So L and tau are reparameterization invariant. Parameterization invariant. Right? They don't change under our choice of how we parameterize where we are along the curve. So for example, suppose we chose S of t instead of t to parameterize our curve, to parameterize where we are along our curve, then the new tangent vector a little exercise for you is SA is dt ds ta. You pretty much have to go to charts. That's one way to get convince yourself of this transformation law. And so now the length, let's define the length. Let's just suppose we have a metric with positive signature. So the length defined with respect to this new parameter s is, well, L prime is per definition just the integral of the square root of GAB SASB, where s is the new tangent vectors. But let's substitute for what we know. So we know that the new tangent vectors are equal to the old tangent vectors times by this whatever delay factor t dt ds times ds, but that's just equal to L. So in fact, the length of the curve doesn't depend on what kind of parameter we felt like choosing to tell us where we are along the curve. So now comes the claim, right? This is the reason we're talking about lengths of curves, amongst others, and that is that geodesics have a very beautiful property, namely they extremize the length of a curve joining 2 points. So that's the claim that we're going to investigate now. We're not going to completely prove it, but we will investigate the claim and to see what we can learn. Once I show you this argument, you should be content to generalize this to the most general setting possible. Okay, to make this life simple, we're going to suppose P and Q are in a common chart, just so we don't have to keep changing coordinates to get from one point to the other. That would be a bit awkward. So a chart is just a map from M to Rn. And to make life even simpler, we're going to assume that C is space-like. Otherwise we have to deal with the proper time. It's okay, doesn't make any particular new challenges for us. Did I put the minus sign in the proper time? Yes, I did. Okay, where C is space-like. And then we're just going to, we have to use a definition for the length. I've got to name that definition, let's call it star from now on. So then star, the length of our curve, in this case geodesic, is the integral from A to B of the sum G mu nu so now we're working in a chart and with coordinates. So C, the curve at the point parameter value A is P, and C, the curve with the parameter value B, is Q. And because we're working in a coordinate chart, the tangent vectors now in this coordinate chart are dx mu dt. So that's just the tangent vector from before. Now comes, so I'll draw a little picture just so we got a concrete setting in mind here. Here's M, here's P, here's Q, here's a chart. Draw that with grey here that contains them. And then I'll draw Rn underneath. There's our chart. Then we'll draw the points P and Q in this coordinate system. P is Q. We have a curve that's connecting them. Here's C. Here's our curve here. Actually, it's a bad picture to draw. Here's C, which was our potential geodesic. And I think that's all we need right now. And now the next part of the argument is we're going to imagine that we vary this curve slightly. So imagine that instead of computing the length for the curve C, we're going to compute the curve for a little variation of that curve. So we vary the curve away from the endpoints. So at the endpoints we actually leave the curve alone. So let's just consider a new curve and look, compute the length for this new curve. So this is the green curve is a variation, is an infinitesimal variation. Right, of psi compose C if we're being super proper. So what does that mean? That means that the trajectory in our chart of our geodesic is actually varied to a different trajectory, namely x mu plus some little teeny infinitesimal variation, which is the thing I've drawn in green. And where, just for some, where we actually demand that dx mu at the endpoints, so dx mu a equals dx mu b. We're not going to vary the curve at the endpoints. We're only going to vary it in the along the length of the curve, but not at its endpoints. So then you can ask the question, you know, how does the length of C prime of the varied curve change? If you do a little variation in the curve, then the length's got to change, and it'll change to first order and so on. We'll just collect terms to first order because we're doing things infinitesimally. Infinitesimal just means we work to first order and then take things so small that the second order terms can be made arbitrarily small. So if you substitute now the new coordinates of the new curve, the varied curve, if you substitute those into our expression for the length, well, then you get a new term. You get a new length, right? So put this into a length formula. Length depends on the curve. So the length, if you substitute this new curve, this varied curve into the length depends on this new curve, right? But if you expand to first order, what should happen is you should get the length of the original curve plus some first order shift in the length. Right? The length's got to respond to the small variation in the length of the curve. And there'll be higher order terms, but we won't focus on those. So what's the first order shift in the length? You know, how does it change when we slightly vary our geodesic? Well, the answer is this. You just got to do some Taylor expanding, and then you'll end up with this expression here. So this is a calculation that you will be assumed to be able to do. Just the Taylor expansion of the length formula, but this is one of these things where, although it's just a Taylor expansion, it can slow you down in your studies if you're not able to fluidly just do these kinds of calculations. So this is just really, I could do all the steps for you. I'm not going to, because I'm a big believer that you should exercise yourself with these little calculations. And therefore I'll leave this as an exercise. So this is how the length responds to a tiny variation of the geodesic. So to make life for us a little bit easier, let's assume we've chosen a parameterization where the tangential or the infinitesimal norm is actually 1. Now, can we always do that? Let's take a look. So if we go back to here, note that whenever you reparameterize a curve, so you choose a new parameter s, then the new tangent vector can be computed according to this formula here, where we've differentiated instead of with respect to s, but with respect to t. And dt ds, well, s is pretty much an arbitrary monotonic increasing function, right? S is pretty much allowed to be whatever arbitrary monotonic increasing function you so choose. And therefore, so I'm going to draw a cartoon of s. Since s is arbitrary monotonic increasing function, then you're able to choose this monotonic increasing function always at every point along the curve, so that the length of the tangent vector is always 1. Just so you should convince yourself of that fact. And so that's why we can assume this from going forward. That just makes life easier for us. Remember, the length doesn't depend on the parameterization we chose, so we may as well choose a nice one. Now, let's test, are geodesics special when it comes to length? So extremality, what does that mean? That means that if you compute the change in something, that change is 0 at a point. And the point in this case is a curve. So you've got to remember L is a function, we're doing variational calculus here, is a functional of functions, right? i.e. curves. So L, the length, is a machine. You give it a curve and it gives you a number. And so if you the space of inputs to the machine that is length is the space of all curves on a manifold, or all sufficiently smooth curves on a manifold. And you've got to imagine there's a huge infinite dimensional space, and L is some functional on that infinite dimensional space. And for a given curve that's a point in this huge infinite dimensional space of all curves, you can evaluate dl and ask, is the variation in the length 0 or not? And of course, we're going to discover that for geodesics this is the case. Now, but we're going to do it sort of backwards. We're going to say, let's just impose extremality. Let's suppose that dl is 0. Then when we make this supposition here, we set the left-hand side of the change in the length to 0. But that expression then leads us to the following equation that must be satisfied by the curve. Right? Not any curve has an extremal length. What sort of curves enjoy extremal lengths on a manifold? Well, you can think it through. You can set the left-hand side of this variation dl to 0, and then you should be able to convince yourself that the only way that can vanish, that variation in the length can vanish, is if the following equation is satisfied. Again, little exercise. This exercise tests your fluidity with calculus and tensor manipulations. There's the expression. I mean, if you look at the equation for the variation of the length, you should hopefully convince yourself, right, that the variation of the length has some derivatives in it, and you should know about integrating by parts to get rid of derivatives off the variation, and then you should try and make it true for all variations, and then you should end up at the equation I've just drawn here. So I'll actually put that extremality means dl is 0 for all variations, right? I didn't really say that explicitly, but I hope that's kind of implicitly clear, was implicitly clear, that if you vary the curve, the length is extremal if no matter how you vary, so for all variations dx alpha, that you get dl equals 0. So imposing that should convince you that the following equation is true. But this is just the geodesic equation. So if you have a geodesic, then certainly it extremizes the length between 2 points. And if you have if you want to extremize the length, then the curve that does that is a geodesic. So this is an equivalent characterization of geodesics, one that's potentially intuitively nicer. Let's write that out. A curve extremizes the length if and only if it is a geodesic. Okay, that's pretty cool, right? And there's something really magical about this, and that is that, let's go back to this picture up here. No, let's go to the one here. So you've got 2 points on the manifold M, and you've got a curve on the manifold M joining the 2 points. And we just concluded that if you draw a curve between P and Q of minimum length, then it's a geodesic. Sorry, extremal length. And this is the key point that I do want to get back to in a minute. If the curve you draw between P and Q is extremal, then it's a geodesic. But a geodesic satisfies a local equation. Right? You can start at P and you can solve for the geodesic that goes from P to Q. As long as you know the tangent vector, the right tangent vector poking out from P, you can solve for the whole curve locally, bit by bit. So somehow the geodesic equation knows about the global structure of the manifold. Now, it's not strictly true, right? Because you needed to know that starting tangent vector. You needed to know which direction to exit from P so that you'll land on Q. So that is implicit in there, a little bit of global information about the manifold. But it's still really striking that a local parameter equation, the geodesic equation, can somehow know with very minimal data about the general structure of the manifold around the point where you're exiting from. I still find that kind of magical. So there's some neater things to know about geodesics. So you didn't have to use the length. You can extremize not only the length to get a geodesic, but actually you can get the geodesic equation from other functionals. You can get the geodesic equation by varying the following Lagrangian. So the following Lagrangian. So this Lagrangian is super simple, right? You just take the tangent vectors to the curve and compute the inner product. And by varying this Lagrangian, obviously you have to integrate it along S, or T, sorry, the curve parameter, you also get the geodesic equation is satisfied. So the minimum of the extremizer of the length is the same as the extremizer of that Lagrangian there. And why do we like this? Because this is really useful, can be really useful. Because it can give a very efficient way to compute Christoffel symbols. It's one of these little tricks you should bear in mind. So you know how to extremize a Lagrangian, right? You need the Euler-Lagrange equations, dl dx mu minus d dt dl dx whatever d mu dt. So that's how to extremize a Lagrangian, and that's like a pretty, you know, if you've got the metric and you look at that expression, then that might be an easier task, right, than going in and just directly computing the Christoffel symbols. Now I want to talk about the word extremize versus minimize. So extremize, right, this is a really important difference versus minimize. So extremizing sounds like minimizing, but it's very different. So if you've got a function, even in one-dimensional function minimization, you should see the difference. Here's a function. This last bit I want to get right. So as it goes up, it goes down, and then it has a turning point like that. Yep. Where are the extrema for this function here? Well, the extrema is where the function doesn't change anymore. So this is where df equals 0. So this is the graph of f versus, say, x or t. Yeah. And here's another extrema down here. df is 0. And here's an extrema here. I didn't really do a good job of drawing it, but no, I didn't do a so good job of drawing it. Well, let's just stick with even this is enough to make the point, right? You have a function like that. There's two extrema. Only one of them is the minima, and things can get really bad. So you think, okay, I've extremized the function, therefore I found the minimum. No. Right? You found a maximum maybe, or you found a minimum, or you may have found one of many local minima. The function could look like that. And you can have arbitrarily nasty many local minima. These are all extremas here that I've drawn. You could have ended up in one of these local minima when you extremize, right? This is all of these points here satisfy df equals 0. So it's a necessary but not sufficient condition to be at a minima to extremize something. And for the specific case of Lorentzian manifolds, so for Lorentz signature manifolds, I'll just tell you a little bit about what extremal curves look like. So you might think that you found a curve with minimum timelike distance. But note the following. It turns out that if you've got 2 points that are timelike separated, then they may have arbitrarily small proper time. So proper time, if you try, you can always minimize the proper time. You can bring it down to essentially 0 always. And how does the argument go? Well, suppose you have 2 points and they're timelike separated. So P, Q. I'm not going to draw the light cone on there. You just have to imagine that they're timelike separated. Okay, here's a curve that joins P and Q. That's going to have a non-zero proper time, this curve. But look at this radical curve I'm about to draw here. This is also a curve joining P and Q, and it's it's physical, it's nearly null, and then it flips around to pointing nearly at the speed of light here, and then flips around to going nearly the speed of light here, and then goes up and goes nearly the speed of light here. That actually has a lower proper time, because along these nearly null segments, the proper time is arbitrarily small here, here, and here. So this gray curve has smaller proper time. So beware of thinking of the proper time as somehow measuring the length of a nice smooth geodesic. Curves that make the proper time lower can be made quite nasty by making them go nearly the speed of light. So I'm not going to prove that statement. It's just an observation that you'll have to believe or investigate yourself. So what do you get when you compute the geodesic equation for a timelike curve? So a timelike curve is a geodesic if it has the greatest possible time. Sorry, I said it the wrong way around. So if a curve of greatest proper time exists, that extremizes the proper time, right? Because it's the greatest. The greatest means that any variation can't get bigger. It must be a timelike geodesic. But because of this very simple one-dimensional calculus commentary above, just because you have a geodesic doesn't mean that it is the curve with the greatest proper time. So if you have a geodesic that goes from P to Q, it need not maximize the proper time. Okay, that's just some warnings about variation of calculus and maximizing and minimizing things. Be careful about thinking that extremal points are minima or maxima. Or quite often they're just local minima or local maxima. Our next topic is that of curvature of manifolds. So we've now reached the point where we've assembled enough mathematical foundations to be able to discuss in an intrinsic fashion the curvature of a manifold. And this is a key ingredient in Einstein's general theory of relativity. So for the next lecture, we will discuss curvature, and I'll give you two characterizations of curvature that are intrinsic to the manifold, don't require that we know the embedding space in which the manifold lives. And at the end of the next lecture, we'll have assembled enough mathematical constructions and definitions that we'll be able to finally move on to discussing Einstein's general theory of relativity. So the main observation, and I've said it enough times in the past, but it's worth emphasizing because it's such a key ingredient, that the main characterization of curvature that we're going to use is that that parallel transport may be path dependent. And that the path dependence of parallel transport is a key intrinsic signature of curvature. So if you parallel transport a vector from the tangent space at some point P to the tangent space at some point Q, then this gives an intrinsic, right? It doesn't depend, parallel transport doesn't depend, and vectors don't depend on knowing if your manifold's embedded in some other manifold. It's an intrinsic proxy or signature for curvature of M. And that's the main observation that forms the basis for the Riemannian characterization of curvature of manifolds. So what we're going to do is we're going to define a measure of curvature, like how curved is a manifold, as the failure. We're going to define this measure to be the failure of successive parallel transporting operations to commute. And that'll define, we'll find a way to obtain a tensorial quantity. So the Riemann curvature tensor is going to be that thing defined by the failure of successive parallel transport operations to commute. That's how we're going to define the Riemann curvature tensor. We'll find a way to do that mathematically. And we'll do this. I'm going to do this derivation one time with derivative operators, and then I'm going to effectively do the derivation a second time with successive parallel transport operations. So that's the physical intuition that lies behind the Riemann curvature tensor. It's the failure of successive parallel transport operations to commute. The actual mathematical definition of the Riemann curvature tensor is in terms of derivative operators. The way to translate between these two definitions is to think of parallel transport operations as being infinitesimal parallel transport operations as being one-to-one correspondence with derivative operators. So what we're going to do is we're going to start by studying the action of not one but two covariant derivative operators on an arbitrary dual vector field omega, well, I know C. And to make this conclusions, to bring them out the quickest, we're going to suppose we additionally have a arbitrary smooth function f. So you really got to think of delta A, delta B as kind of being two infinitesimal parallel transports. So let's consider the following expressions. Delta A, delta B applied to f omega c. So if C is a dual vector field, then f times omega c is a dual vector field. And we're going to try and parallel transport it along one vector direction, which is indexed by slot A, and another vector direction, which is indexed by slot B. And to carry out this computation, we just use several properties of the derivative operator delta A. Firstly, we're going to use the Leibniz property and the fact that on scalar functions it reduces to the normal derivative. In fact, no, we're not even going to bother using that. We're going to use just the Leibniz property here in the first line, and then we just use Leibniz property again in the second line here. So we can get 4 terms depending on where this delta operator lands. Okay. And note that this is going to enjoy some interesting properties. In particular, the first term here, because we've assumed our derivative operator is torsion free, we know that delta A, delta B, F will be the same as delta B, delta AF. And the two terms in the middle, had we done B then A, well, we would have gotten the same two terms in the middle. And in fact, the only term that would differ between, if we had changed the order of these parallel transport operations, is the last one. So that's, I've already essentially given you the proof of the next statement, the one that really will characterize the Riemann curvature tensor. Let's consider the difference of doing a teeny infinitesimal parallel transport along the A slot vector and the B slot vector. The difference of doing it one way and the other. Well, it's a little exercise where I've basically told you how to do it. You note that this is true, right? you see that the difference of these two derivative operators when applied to f omega c is the same as f of these derivative operators applied to omega c. But we've seen that before, this kind of structure. You know, when we were talking about derivative operators, we considered their actions on scalar functions multiplied by dual vector fields, and we saw that the action of a derivative operator commutes with a scalar function f, and then we applied a intermediate mean value type argument to show that delta A omega B depends only on the value of the dual vector field at the point P under consideration. The same reasoning applies here. So, since this is true for all f, we learn that delta A, delta B minus delta B, delta A, omega C only depends on the value of omega C at the point P where you are, right? That's the key consequence of this little computation. So now we learn that the commutator of these derivatives defines a map I'll just write it out as a map from tensors of type 0, 1 to tensors of type 0, 3. And in other words, there exists a matrix representation for this linear map. R, A, B, C, D, which is a tensor of type 1, 3, such that for all dual fields, we have the following representation. And now I've just defined for you the Riemann curvature tensor. It does turn out to be a tensor in this case. So R, A, B, C, D is something called the Riemann curvature tensor. And mathematically, you can see it sort of measures the difference in parallel, in making little infinitesimal parallel transports along two directions. Now, that intuitive interpretation of this mathematical equation can be made more precise, and that's what we're going to do now. So I'm going to give, I'll give a argument now to you that will relate R, A, B, C, D to the failure of successive parallel transports. And to do that, I'm going to draw for you a picture to explain this. So we'll put a slightly orange. Now, what you've got to imagine here is that we've got a manifold M, which is this, which I've now drawn as a three-dimensional manifold. Here, M is, for the next part of this argument, you've got to imagine it's important that we have, you think of the manifold as being higher dimensional than just one. So, in particular, it's very important that M in this characterization looks maybe arbitrary dimensional. So M here is this orange surface, orange volume, right, in this story. And then what's going to happen is we're going to talk about successively parallel transporting a vector in two different ways. So we're going to start with some point P, and P is in a surface S. It's also in a big manifold M. And what we're going to imagine is we start at P and that there is some two-dimensional surface S that P lies in as well. This is really important. And we're going to parallel transport our vector along one curve in S, along another curve in S, along another one, and then back to where it started from. So suppose you have a vector V at P, and then you parallel transport it along one direction in your two-dimensional surface. And then you parallel transport it along this next part of a little square that you've drawn in your surface. And then so on, you parallel transport it back. And then, I don't know, at the end of it, you end up with a new vector V prime, which is the result of having parallel transported your vector around this little square inside this surface S of dimension 2. So you've got 4 portions to this parallel transport, right? Depending on where you're going around this little square. And we're going to make things a little bit easier, we're going to coordinatize our manifold and say that these portions are on constant coordinate lines. So that this little square is in this little square is realized by doing a little transports along constant coordinate curves in the surface S. I'll write this out in equations in a minute. So the coordinate of the point P is 0, 0. The coordinate of the first point on the journey is 0, delta t. So we have 2 coordinates. Of the surface S. Now, of course, M has n coordinates, but S is a two-dimensional surface defined by 2 coordinates. Just to call them little s, little t. So this is big S. And the second point on our journey is delta S, delta t. I could put deltas in there. Sorry, shouldn't have done that. The second point in our journey is delta S, delta t. The third point in our journey is delta S, 0, and the starting point is 0, 0. So we take, now you see the data, what do we need to what data is required to even set up this scenario? We need to have a surface. A surface is defined by maybe 2 vectors, right? You can imagine that it's a kind of flat surface defined by 2 vectors. So to even talk about a surface in a manifold, you need the data of at least, say, 2 vectors, right? You also need the data of another vector V. That's the vector that's being parallel transported around this surface. And you need the metric, and you need a covariant derivative operator to talk about this scenario here. So now let's write out, that's the picture of the scenario I'm now about to describe. So in slightly more precise words and equations, so we consider a loop starting at some point P in the manifold, and this loop is defined by a two-dimensional surface S through P. And so the coordinates, we can choose some coordinates that we like for S. Let's just call our coordinate system whatever, S, t. And of course, in the picture above, I've made it clear that the coordinate system, that the origin of this coordinate system is exactly the point P. Then the loop that we're going to parallel transport our vector around is defined by the following 4 steps. We start at the point 0, 0 in coordinates on S. We go to the location 0 delta t by path parallel transport operation 1. We go to the location delta S delta t by parallel transport 2. We get to delta S comma 0 by 3. And then we finally end up at 0, 0 by parallel transport 4, finishing our path. So to do this parallel transport, well, we're going to need a vector. So let V be a vector, an arbitrary vector, right? Not just any vector, an arbitrary vector. And we're going to parallel transport it around the loop. And to make the computation a bit easier, we're going to suppose we have an arbitrary dual vector field defined everywhere on the manifold. This is just helpful for the computation, you don't need it. What the style of argument we're going to use is we're going to construct a scalar quantity and consider that, and then parallel transport the scalar quantity around, and then it just is easier to do the computation. And then at the end we let omega a be arbitrary and cancel it out. So omega a just plays the role of turning of like an arbitrary test dual vector. So now to actually do our computation, we consider VA omega A, and now that's a scalar function on the manifold, and that makes some operations a bit easier to do mathematically. Now let's look at the change in this scalar function along the first part of our little loop. How is it defined? Well, we're going to make an infinitesimal loop, or said equivalently, we just consider things to first order. And now here's something that may throw you for a second. We're going to evaluate the first order change at the midpoint between the point where we are and where we're going to end up. Now, of course, I said first order up to now, but I lied. In fact, we're going to do this computation to second order. This is one of these rare occasions where you do need to go to second order. So evaluating this expression for the change delta 1 in this scalar function VA omega A, if you evaluate that at the midpoint, you actually get an expression that's correct to second order. Even the second order term is correct. That's a handy trick to know. If you have to do a calculation that's correct to second order, you could either include the second order term and evaluate it at the endpoint, or you could take just the first order term and insert the midpoint here. It's pretty a neat and handy trick for doing calculations to second order that you should remember. So delta 1 is big delta t, t, b, d delta b, v, a, omega a. I'm just using the fact that on scalar functions, the derivative operator reduces on scalar functions to the normal derivative operator. And then if we just apply Leibniz property and use the fact that VA is parallel transported, then we get the following expression. delta 1 has this expression. Oh, I mean, maybe not. I better make it explicit. Here TA is a tangent vector. It's not A, it's D. It's the tangent vector to the curve with constant S coordinate. And parallel transport operation means that TA so similarly, just do the same argument. We obtain for the change along the third part of our journey the following expression, right? On parts 1 and 3 of our journey, we're changing the t coordinate. So all that changes between these two expressions is where you evaluate them, namely at the midpoint of these two coordinates. So then what we're going to do is we've got two parts of the change in our function along our parallel transport around the loop. Let's combine them, and then I'll leave the other two as an exercise. It's just going to be an exercise in changing s's with t's. So I'm just going to add them up, right? Subtract them, sorry, or add up the first term and to the inverse of the second term. And we're going to call this stuff later. We're going to give it a name, but right now we're not. And we're just going to notice one thing about this expression, right? As a function of delta s, this vanishes as delta s goes to 0. As it should do, right? You know, if you parallel transport along a curve and then go back the way you came, you better get 0. And interestingly, if you go through the computation and work out d2 plus d4, then you see that it goes to 0 as delta t goes to 0. So actually what we've learned is that parallel transport around a loop is path independent to first order. So parallel transport around a loop is path independent to first order. I mean, it's definitely path dependent, it's just path independent to first order. So the path of dependence appears at second order. So now our goal is to get the path, the second order dependence on parallel transport to second order, by explicitly isolating out the second order terms. So to get second order dependence, consider the parallel transport of our vector VA and of a second vector, which you can define, a covector, dual vector, along t equals delta t, or along, yeah. This is a weird device, what we're about to use, but I'll draw a picture to try and explain the construction here. So here's our vector v that we've parallel transported up to the midpoint. And now we're going to parallel transport along this dotted line here. And this dotted line is the curve t is delta t over 2, not delta t. So here's the point delta t, 0 delta t, here's the point delta s, delta t up here. Here's the coordinate 0, 0. So we're parallel transporting VA along this mid-curve. So we're not going to parallel transport it all the way around the loop. We're just going to send it up to the mid-curve. And we're also going to parallel transport this other vector, this covector, dual vector TB omega A along the same curve. Why are we doing that? Well, because if you look here at the difference, delta 1, delta 2, you notice that we're evaluating things at midpoints, right? And what we want to do is we want to compute the difference between these two terms that I've highlighted in yellow. VA is of course common here. So you can pull that out as a common factor. We want to evaluate the difference of these two yellow highlighted terms. And, well, they're evaluated at different points in the loop. In fact, VA, although VA, I said it's common, of course it isn't, right? VA here, the second blue one, is evaluated at the other point in the curve. So I've got highlighted in green. So we want to get, in order to actually compare these two quantities, well, we need to evaluate them at the same point. And here's a trick to doing that. So we imagine we're going to parallel transport the yellow dual vector, yellow highlighted dual vector, to the midpoint of the part 3 of our parallel transport. And then we'll just mathematically subtract them at that point there. Now, we've already determined that to first order, the vector VA at delta S delta t over 2 is equal to VA at at 0 delta t over 2. Because parallel transport is path independent to first order. So the only quantity that does change along the red dotted curve is TB delta B omega A. So at delta t over 2, it differs from the same dual vector evaluated at delta t. Oops, did it the wrong way around here. Put the delta S first. Right, these two quantities potentially differ. In fact, they almost certainly differ because omega A is an arbitrary dual vector field on the loop. And this quantity differs from, yeah, obviously it differs that, but we can't compare these two quantities yet. They're at different places, so we have to parallel transport them. So it also differs from this dual vector field parallel transported to delta S, delta t over 2. And how does it differ? Well, just go back to your defining properties of parallel transport and work out that to first order, the parallel transport of a dual vector is given by the formula. The first order is given by integrating the equation of motion for the parallel transport of a dual vector. You can do it to first order. So I'll just leave that as an exercise. And we're now parallel transporting along the constant s coordinate. Constant t, sorry. Call this star star. Substituting star star into the expression for delta 1 plus delta 3 now gives us our desired second order dependence. And similarly for delta 2 plus delta 4. Now, let's put them all together, right? We need to understand what the total change is as we go around the whole loop of our quantity VA omega A. And, well, exercise, it turns out that when you add up the change over all the 4 legs of the journey, that you end up with the following expression. I think I've got a bracket too many. No, looks right. And now let's rearrange things. And we'll see that we get quite a familiar expression. Namely, we get the commutator of these two derivative operators applied to the dual vector. Now the reason why I could go from the first line to the second line, well, I'll get to that in a sec, but I want to highlight, of course, that what comes out is that the second order dependence of the change in parallel transport of vector V is dependent, it is controlled by the Riemann curvature tensor. So, but how did I go from lines 1 to 2? So here we used the fact that for coordinate vector fields, that the Lie bracket vanishes. Which in our case was dds and dt. So we've learned that this variation delta VA omega A, now there's a bit where we cancel off this dual vector field, it can hold for all omega A only if to first order, or in delta S and delta T separately, or more correctly to second order in delta S, delta S and delta T, that the variation, the path, the difference in the parallel transport of delta of VA around these two legs, or around the whole loop, obeys this equation here. And this gives us our second interpretation of the Riemann curvature tensor. You know, the first was really as a mathematical definition. The second here is as the failure of successive parallel transformation operations to commute. So this concludes this lecture on geodesics and the Riemann curvature tensor. In the next lecture, we're going to continue our discussion of curvature and establish a whole bunch of properties of the Riemann curvature tensor. We're going to introduce some derived quantities, and we're going to relate, in the most important consequence of this discussion, we're going to relate the Riemann curvature tensor to the divergence of nearby geodesics. But that's it for now. Thank you and goodbye.